In this session, we want to look at the geometry of vectors. In applications, many things can be described by a single number. Such things are going to be called scalar quantities. For example, length, volume, mass, and temperature. They're all going to be defined by a single number, and they are going to be called scalars. Whereas in other applications, you might need two things to describe an object. You might need magnitude and direction, and such things will be called directed quantities. So, for example, velocity and force, displacement and acceleration. These things are going to be called vectors. So a vector has both magnitude and direction. A vector in the plane can be represented by a directed line segment. If we have an initial point A and a terminal point B, then we say and denote the vector from A to B with a little directed line segment above it, denotes that vector in the plane. In books, you might see a vector denoted by a single letter V or W with a line above it. Sometimes you'll see the vector by a single letter, but that letter would be in boldface. We would denote the length as a pair of absolute value bars around the vector. The zero vector has no displacement. And we can define the opposite vector. So if this is my vector here, V, the opposite vector would have the same length as V, but go in the opposite direction. Two vectors are equal if they have the same direction and the same length. So for example, if we have our coordinate system, and if we have the vector, let's say this vector up here in the first quadrant is vector u, then we can create many different vectors that are equivalent to that vector u. As long as they have the same length and the same direction, it could be anywhere in the plane. So all of these vectors are going to be equivalent to that vector u. In other mathematics courses that you'll take later on, you'll see this idea is the forms a vector field. Now, vectors are going to be useful in answering questions like the following. Suppose you wanted to get across a river, and there was a current in the river, and you wanted to go from the shore to the opposite shore. Now, how would that current affect the motion of your boat? And you would like to figure out what kind of course correction do you need to do to end up exactly on the opposite end. In answering questions like that, we're going to look at the idea of one displacement followed by another displacement, starting at initial side A and going over to terminal side B here. So there's my vector AB, and then I have another displacement starting at B and going off to C. There's the second vector, BC. The net result is the vector formed by starting at A and going off to C. So AC is equal to AB plus BC, and it's called the resultant, or the sum of the two vectors. So that tells us when we add vectors together, we want to add vectors tail to head. So if we have the two vectors, say, in standard form here, anchored at the origin. So if this is vector u, and let's say vector v is over here in the second quadrant, then we would take the tail of vector v and append it to the head of vector u so that we have the same direction as vector v and the same length as vector v, and completing the side of the parallelogram. Then the resultant is found by taking from the origin and going across the diagonal as the vector u plus the vector v. Now suppose we let c be any real number. So c is going to be a scalar, and let v be a vector. We define the product c times v, which will be a vector in the same direction as vector v, but scaled. So it could be a contraction or a dilation, depending on the value of c. It could also be in the opposite direction, depending if c is negative. For example, if this is the vector v, then what does 1/2 v look like? Well, 1/2 v is going to be a vector starting at the same terminal edge and going in the same direction, but only half of the length. It would be 1/2 v. And if this is the vector w, then the vector 3w would have the same direction, but 3 times the length. Here's an example. if this is our coordinate system, and let's say the vector u is over here in the first quadrant, and let's say the terminal side of vector u is at 1, 3. And let's say the vector v is in the second quadrant, and the terminal side of vector v is here at -3, 3. Question says, find u plus v. We want to take the tail of vector v and place it at the head of vector u so that we keep it the same direction and length. So this would be up here, vector v, and completing the side of the parallelogram, that side would be vector u. Then the resultant vector, the sum of the two vectors, u plus v, is found by going from the origin and tracing across the diagonal of that vector. And it looks like the resultant vector has terminal point up at -2, 6. Next question says, what does the vector 1/3 of v look like? Here's our coordinate system. Remember, vector v was going from the origin to -3, 3, and 1/3 of v would be in the same direction except a third of it. So if this is 1/3, 2/3, third, 3/3. So 1/3 v is down here. -1, 1 would be the terminal side of 1/3 of v. And if we look at what would the vector -u look like? Well, -u would be in the opposite direction of u and the same length. U has terminal side up at 1, 3, then -u would have terminal side at -1, -3.